All right, in this problem, we have an established buffer, 0.3 moles. This is a 1 liter, so we read it as 0.3 molar, HF, 0.2 molar of our common ion, NaF or F minus. Right, so it starts out with this. We have HF that would be reacting with water to form H3O plus and F minus. However, and so if we had an ice table, we would say, we have 0.300 here, 0.200. However, we have this going on where we have 0.1, for me, 0.1 molar of NaOH being added. So what is that going to do? That's going to, this is a strong base. It's going to react with our weak acid. Now, if we were adding HCl, it would react with the F minus, but our conjugate base, but we're adding a strong base. So that looks like this, right? HF plus, the Na will go in as Na plus and OH minus. This is our base part. So reacting with H minus forms H2O and F minus. So what we had was 0.300. We're putting in 100 of this, and we started with 200 here. And so what we're going to do, and what we would do in an ice table here, is show what we're doing. So what we're going to do is we're going to use up this OH. It's going to react with this, and it's going to create here. So this is kind of like X, right? So we could have written plus X, minus X, minus X. And our X, we just know our X, which is 0.100. So we're going to end up, so this is our ice table, right? At 0.200. Water, we don't care about because it's pure, and 0.300. So we started out with 0.3 and 0.2, and now we're down to 0.2 of HF and 0.3 of F minus. We gained F minus. So now we could solve for this two different ways. We could do our ice table, solve for X, but what we're going to do is use our Henderson Hasselbalch equation and do our log of our new components. So base over acid. And we got pKa is the negative log of 6.8 times 10 to the minus fourth, which is 3.167. And then log of 0.3 divided by 0.2 is 0.176. We add those up, 3.16 plus 0.176. We get 3.343. So I'm going to do 3.34. Another way to write it would be just without doing this, if you can just kind of visualize this, would be pH equals pKa plus the log of our original, so 0.200 of our F minus, which we saw, up here, plus 0.100 on the top, and then here we had 0.300 and we minused 0.100. So same thing, but this, and I think this is how they'll show it when we look at the answer here, but this is indicating the change without writing out this large ice table. There are other problems where it'll actually want you to write this out, this ice table with the reaction of OH minus, and then you will have a second table, which is the other way to solve it, right? So if I want to solve, so 3.34, if I want to solve the other way, I could do H3O plus. I could say, okay, now I'm starting with 200. Right, this is after my adjustment one where it reacts with OH minus. I'm at this, now I could say, I'm gonna subtract X. Oops, sorry, this is a 0. I'm gonna plus X. Then I'm gonna set that equal to Ka. I'm going to do my X is small. So X times 0.3. That's equal to 6.8 times 10 to the minus 4th. So 6.8 times 10 to the minus 4th times my 0.2 that I'm bringing up here, and then dividing by 0.3. And so I get X is equal to 4.53 times 10 to the minus 4th. The negative log of that is 3.34. So two different ways to solve it, right? I can use my ICE table. This is my ICE table after that original one, right? Where I reacted HF with OH minus to determine how much F minus I would have. And then I set a new ICE table. There's at least one problem where it'll have you write that first table, OH minus reaction with the weak acid. Then you'll do a second table that will look like this. And then you'll set it over Ka, and then you will solve for pH. So look for that problem as well. Let's put in our 3.34. There we go. And they show Henderson Hasselbalch.